Hello and welcome to this fourth installment of our video series on quantitative data analysis using non-parametric approaches. Continuing from the last segment, we looked at univariate hypotheses and how to test whether one of the variables or columns in our data set relates to some theoretical value. Here we'll look at multivariate hypotheses and we'll see how we can test whether two of our variables or two of our columns in our data set, whether they are related to each other. As with the univariate hypotheses, the statistical test that you choose in JASP will depend on the type of variable that you have. The only difference being here we are differentiating further between nominal variables with 2 levels and nominal variables with 3 levels. You'll see why as we go along. The table allows us to combine any type of variable with any other. So let's start with the first column. So if we have a scale variable, if we're relating it to another scale variable, that means that we choose the Spearman test. If we have a scale variable and we're relating it to a nominal variable with 2 levels, we choose the Mann-Whitney test, and so on. There's a total of 4 tests here. Let's go through each one of them in turn. So in this data set, we've got mark that students get in a quantitative data analysis test. We've got the course that they're in. These are all courses in our own institute. We've measured their gender, and we've also measured their interest in quantitative data analysis. So we have scale, nominal, and ordinal. This nominal variable has 2 levels. This nominal variable has 4 levels because there are 4 courses. Now the variable I've added on, this is also a scale variable. I've added this on simply so that we can look at the hypothesis testing between 2 scale variables. So what this variable is, it's the overall mark that the student gets in all of their other units. It's the average mark in all units except the quantitative data analysis test. Now I'll remind you, this data is fictitious. I've generated this myself purely for the sake of giving you an example. Now, the mark overall has been recognized by JASP as an ordinal variable. We need to change that to a scale variable. So what I would like to do in this first hypothesis, we're going to use an example, is to see whether the mark that they get in the quantitative data analysis test is in any way related to the mark they get overall. So if they get a high mark overall, does that also mean that they'll get a high mark in the quantitative data analysis test? If they get a low mark overall, does it mean that they'll get a low mark in the quantitative data analysis test? When one goes up, does the other one also go up? Or when one goes up, does the other one go down? That would be an inverse relationship. So the question really is, do they vary together in some systematic way? Can one help me predict or explain the other? That's really what we're trying to establish when we're running our hypothesis. More specifically, as we did in the univariate hypotheses, we'll be looking at the null hypothesis. So we'll be testing the idea that these two are not related to each other. That is ultimately what the statistical test is going to investigate. So how do we correlate these two variables? We have scale with scale, so this means that we need to choose the Spearman test. So how do we run a Spearman test? You click on regression, correlation, and as always our panel pops up and we can set up our hypothesis here. Now we're using non-parametric approaches as always, so we're interested in the Spearman's rho rather than the Pearson's R. Now we're doing this because we want to use a robust style of analysis that doesn't require us to make any assumptions about how our data are distributed. So in this case, a non-parametric test for correlating 2 scale variables is the Spearman's correlation coefficient. So we have to put the marks that we're interested in hypothesizing about in our variables box. So we have mark in the quantitative data analysis test and mark overall. Straight away, our table gets populated here. Now, I intentionally put in data to show us what a significant relationship actually looks like in a scale-on-scale hypothesis. So here we can see the p-value straight away, same logic as we had before with the univariate test. It's way below 0.05. It's very, very, very low. So the probability here that I am mistaken in going ahead and assuming that there is a relationship between these 2 variables, that probability is very low. More specifically, it is less than 0.1%. It's less than 0.001. Once we see that we have a significant result, we then look at the strength of that relationship. And the correlation coefficient here is telling us it's 0.89. Rounding down to 2 decimal places. That is a very strong effect size. There are many different correlation coefficients, but they all follow a similar interpretation. Anything from 0.3 to 0.5 would be considered mild. If it's above 0.5, it would be considered moderate to strong. If it's above 0.7, it's strong. Also, I should say this could be a minus value, so it varies from 0 to 1, but it also goes the other way down to -1. So if you have a correlation coefficient of, say, minus 0.89, that would mean there is a very strong relationship, but it is inverse, which means that when one goes up, the other one goes down. So we know here that we can reject our null hypothesis. The evidence here is sufficient to reject the null hypothesis. If we want to represent this in our findings chapter, we would simply say the evidence was sufficient to reject the null hypothesis of no association between marks in a quantitative data analysis test and marks overall. And we put our test statistics in here. So we had RS was equal to 0.89 and P was less than 0.001. As always, we can italicize the statistics. In the case of the RS, we subscript the S. So that's how you would present a Spearman's correlation coefficient. So that's how you present it in text. Now we can also, as always, present this visually. To present it visually, make sure that you click Display Pairwise and then Scatter Plots. And this is going to show us a nice visual representation of the relationship between our two variables, because it gives us each case as a dot, so we can see each individual data point. Take this student, for example. This student scored around 80 in their quantitative data analysis test, and they also scored just above 80 overall. So we're seeing here that as the quantitative data test mark goes up, so too does the overall mark, and we can see the pattern here in the data. If there was no relationship here, so if the p-value was not sufficient and the correlation coefficient was very low, so less than 0.3 or less than 0.2, we would see just a cloud here. So there would be no discernible visual pattern to the dots in our scatter plot. As always, we can copy this and paste it into our findings chapter. So let's look now at nominal against nominal. Now, in this particular case, it doesn't actually make a difference how many levels that nominal variable has. If you are testing a relationship between two nominal variables, they can have any number of levels. The number of levels only really count when you have a nominal variable with a scale variable. So let's have a look at the simpler example first, nominal with nominal. In our data set, we have two nominal variables. We have course with 4 levels, and we have gender with 2 levels. So let's say that we wanted to hypothesize that these two columns or these two variables are related to each other. There is a relationship between them. One will help us predict or explain the other. What this hypothesis would actually be investigating would be, is there some kind of systematic trend in each of those courses with regards to whether males or females choose that course? Another way to say this would be that males or females tend to choose particular courses, and they do so in some predictable way. So to run this hypothesis, we need to choose frequencies, contingency tables, and here we can put our two nominal variables into the rows and columns boxes. So let's put course in the rows and gender in the columns. So the output panel has created a contingency table which basically splits up our participants according to male and female categories in each course. So it's subdivided gender across course. Now, to look at the logic of this test, if there was no relationship between these two variables, so in other words, if the null is true, so if the null hypothesis is the case, then we would expect to find the ratio of male to female, it would be the same for each course. So if we had, say, 2 females in health and social care, we would also expect to find 2 males. If we had 6 in inclusive education females, we would also expect to see around 6 males. Now, I should really say here that one of the assumptions for the chi-square test is that we should really have a sample size that is large enough such that we don't have less than 5 values in any of these cells. So that's one of the assumptions that we need to try to stick to. But in any case, let's look at, for the sake of example, what our test statistic has turned out to be. Here we have a chi-square value of 6.59 and a p-value of 0.09. I'm always, as always, rounding down to 2 decimal places. So what this is telling us is there is no statistically significant relationship between gender and course. So the null hypothesis, this evidence, is not enough to reject that null hypothesis. It's not enough to dismiss the idea that these 2 columns across each of the courses are not equal. We cannot really reject that idea based on this evidence. So the p-value here is basically telling us that there is no relationship between gender and course. So let's look at another combination now. We can look at a scale variable with a nominal variable. We'll take 2 levels first. So let's look at mark in a quantitative data analysis test. We'll see whether this varies by gender. So in other words, we'll see if there is a relationship between gender and the mark students get in a quantitative data analysis test. Another way of saying this would be there is a difference between males and females in the marks they get in a quantitative data analysis test. So how do we test this hypothesis? We click t-test, independent samples t-test, and as always, we choose the non-parametric option, which in this case is the Mann-Whitney test, and we can deselect the students t-test. We input the variables that we want to hypothesize about. So we've got marks in the quantitative data analysis test. That's our outcome that we're interested in. That's our dependent variable. And the grouping variable is the gender. So straight away in this table, we have our test statistic of 35.5 and a p-value of 0.451 or 0.45. So this p-value is telling us that there is no relationship between gender and mark. So there is no difference between males and females in the mark they get in a quantitative data analysis test. The null hypothesis states that there is no difference between males and females. And in fact, the evidence here seems to be supporting that. So we can't reject that. We fail to reject the null. If there was a significant effect, then we would also be able to report the effect size. And in this case, as is explained here, the effect size for a Mann-Whitney test is presented using the rank biserial correlation coefficient. So this is a correlation coefficient just like Spearman's rho, and we can use the same brackets to interpret the strength of the relationship. We can also report the basic descriptives here. So it's interesting to see here what the mean for each group was. So as we can see here for females, the mean was 68.8 and for males it was 73.6. There was a difference, but that difference was not statistically significant. So our hypothesis test, that's precisely what it's telling us. Look, is there some systematic, statistically significant relationship between these 2 variables? A great way to show this visually is to click on bar plots. And this will show us, just like we did in the univariate hypothesis where we used the Wilcoxon test. Here we have the bars showing us the central tendency of each group. In the case of females, we've got a mark between 60 and 80 here, which corresponds to what we've seen in the table at 68. And the error bars, or the confidence bars here, are not really distinctive from the error bars in the males. So this gives us a visual indication of the statistical significance of these 2 differences. If they overlap, we can't really conclude that there is any real noticeable, discernible difference between these 2 groups. Ultimately, the bars combined show us that there wasn't really much of a difference in this case. So this is why it's useful to see the visual. Now, in terms of presenting this in text, you would present it just like we did before. you would say the evidence was not sufficient in this case to reject the null hypothesis, that there is no relationship between gender and mark. And in brackets, you would report the test statistic, which is W. So you would say W is equal to 35.5, comma, P is equal to 0.45. Now let's look what happens when we have a nominal variable with more than 2 levels. So the process is almost identical. It's just that we need to pick a different test. So scale variable with a nominal variable takes us to Kruskal-Wallis. So to do a Kruskal-Wallis test, let's look at ANOVA, and we will investigate mark as our dependent variable. And as a fixed factor, we'll use course. So what this hypothesis will tell us is, does the mark in a quantitative data analysis test vary according to what course the student is doing? So is there some kind of trend going on here whereby students in particular courses tend to do either better or worse in their quantitative data analysis test? So the logic here is very similar to the Mann-Whitney test. However, in this case, we need to pick Kruskal-Wallis rather than a pure ANOVA. To do that, we click on non-parametrics here at the bottom. We need to re-enter our nominal variable here into the box on the right, and that will give us our Kruskal-Wallis results table. So once again, we have our test statistic here, which is W is equal to 0.06. Our degrees of freedom are 3, and our p-value is 0.99. So what this is telling us is there is very little evidence here to suggest that the null is not the case. So we can go ahead and we can accept the idea that there is no difference here. There is no relationship here between what course you do and what mark you get in a quantitative data analysis test. So if we were to go ahead and assume that there was a relationship here, there is a 99% chance we would be wrong given this evidence. We can represent this data visually as well. So if we click on descriptive plots, we can enter course into a horizontal axis here. Now this will give us an indication of what the mean in each group was in relation to each other. And we can include error bars as well, which will illustrate in this case that there is a significant degree of overlap here. So we cannot really conclude, looking at this visual, that these are different from each other. They are all the same, and all the confidence bars overlap each other. And finally, what about the ordinal variables? Now, the ordinal variables here can be treated, as always, either as a scale variable or a nominal variable. So you actually have a choice here. If you treated an ordinal variable as a scale variable, then you could use the Spearman test to correlate it with another scale variable. Or you could correlate two ordinal variables that you are treating as scale variables with each other, and you could similarly choose the Spearman correlation coefficient. So let's give a very, very quick example here in terms of the mark that was obtained and the interest in quantitative data analysis. So here, if we look at the original data set, we had this variable here, which was based on a question. The question was, I am interested in quantitative data analysis, 5 being a strongly agree and 1 being a strongly disagree. So we could hypothesize, for instance, that interest and the mark obtained in a quantitative data analysis test are related. So this would suggest that the more interested you are, the higher the mark you'll get, the better you'll do. Or likewise, the less interested you are, the lower the mark will be. Now here we are treating these two variables as scale variables. We are treating interest here in terms of its quantity. We're treating it in a sense that more of it is equivalent to a higher value and less of it is equivalent to a lower value. So if we wanted to see the relationship here, we would do a Spearman test. So as we did before, the Spearman test is regression, correlation, and include the two variables we want to correlate into the variables box. So we did mark in the quantitative data analysis test and interest, Spearman's, and here we can see from the p-value that there is no relationship, at least in this particular data set, which I will remind you once more is fictitious data. I've generated this myself purely for the sake of giving an example. Now, the p-value here suggests that there is no relationship. There is a 96% chance we would be mistaken if we went ahead and assumed that there is a relationship here. So we cannot really reject the null. We have to accept the null. We fail to reject the null. Likewise, if we wanted to treat interest more as a nominal variable, we could do a Kruskal-Wallis test instead. So if we click on ANOVA and we input interest as a nominal variable, so we really want to see among those who chose strongly disagree, disagree, neutral, agree, or strongly agree, across those as groups, as distinctive groups, do we see a difference in the mark that they got? So we can put mark into the dependent variable box. We scroll down to non-parametrics. Interest goes on the right. And here we can see that the p-value, once again, is above 0.05. Now, there are subtle differences here. In the Spearman test, we were basically looking at, as one increases, does the other increase? We were looking at quantity, but here we're not looking at quantity. We're looking at these as distinctive groups. So if we were to say EQF level, for example, as an ordinal variable, this is the example I gave in the beginning. If we wanted to see, look, is there a difference between those people who are doing a diploma level, a degree level, or a master's level, for instance? Is there a difference here? And if so, where is the difference? That would be a hypothesis that would be interesting to test in either format. We could test, look, does more qualification correspond with a higher mark? That would be a Spearman test. Or we could say, look, is there a difference between the different courses in terms of the mark they get, and where are those differences? Now, if we did have a significant difference here, then we would want to run a post hoc test. So this would be the final thing I'll show you. Now, this obviously applies to using a normal nominal variable as well. So if you get a significant finding, whether it's an ordinal or a nominal variable, you would proceed to this next step. You click post hoc tests. You need to move the grouping variable again onto the right. And here you can choose the done test. And this would give us a breakdown of each individual level combination. As I said, this would be more interesting if the initial result was actually significant. In our case, it was not. So this table explains all the possible types of variable combinations that you can have in your hypotheses and which procedure to select in JASP. If you forget any of the steps, naturally you can check back on this video and you can see where to click to actually run each of these tests. In the next segment, we will pull all of this together and pay a little bit more attention to what we actually need to write in the findings chapter about each of these phases. So what we've been through so far is how to actually do these steps. Now we'll see how we put it all together in terms of presentation and how your final thesis or research report should actually look in practice.